All right, for those of you that are just joining in, I'm going to start recording. And as soon as this is done, as soon as it downloads, I will post it to YouTube and I'll give you guys the link for YouTube. Cool beans. Also, real quick, let's see if I can find it real quick.
Are you going to post the last one we did on YouTube?
Yeah, I didn't do that.
You only post half of it.
I only post half of it. Okay, I'll see if I can, well, I'll see what happened there and I'll see if I can get the other part up. This one is up in Adam. By the way, real quick, you guys see this real quick, the attendance? I'm just marking everybody here, so if you're checking in, regardless of that, I know that some people need the attendance kept for financial purposes like that. And I really can't keep track of if you're popping in or popping out this way online. So I just want to let everybody know that even if you stop in for a couple of seconds, that would be great. I'm marking everybody here for tonight, though. And I'll start doing that now so you guys can see that you guys got credit for last week. I'm not quite sure what they're doing for the weeks that we were off, but I think that will be okay. There you go. I missed a couple, hold on. One, two, okay. Cool, success. All right, let's go back to the problem, the practice zone that we were going to do to start things off. This is it. Okay, so we're in drive-through at Wendy's. Let's see, assuming that drive-through times are normally distributed, that's the key. We're working with a lot with normal distributions, and we will continue to do so tonight as well when we talk about sampling distributions. So this is our parameters. We know that those are the important part is we have shape, center, and spread. Okay, we're still thinking SOX when we're describing our distribution. So these are our important parts. This is the key to being able to do this problem, is being able to pick it apart, being able to anticipate what kind of question are we being asked. We know we have a normal distribution, that is a shape. We are given a center of 138.5 seconds. That's our center, that's our mean. And we use a measure of spread. How much will that vary from car to car? By about 30 seconds, 29 to be exact. Okay? And that's how long we're going to spend in our drive-through. So the first question is, what is the probability that a randomly selected car will get through Wendy's drive-through in less than 100 seconds? Okay.
I'm sorry, do you have this posted somewhere? It's Jessica.
It's up there, it's in Blackboard in the Chapter 8 resources.
Okay.
So if you have a chance to look through.
Yeah, I'll look now. Thank you.
It should say, it says at the top there, this is what it'll be, show up in Blackboard, the classroom examples, okay. Section 8.
Awesome, thank you.
Mm-hmm. And the PowerPoint that I'm also using tonight is also posted. And any other materials I could think of that also are going to be posted. And I also put the homework up for this week. I'm just going to do the same thing I did last week. I'll just do a worksheet with selected problems. I'm not going to overwhelm you. Believe it or not, my daughter is taking statistics right now too for her college, and she's online, and her professor gave her like 128 problems to do for the week. I think that's a little much, but like I said, if you have any questions on what we're doing, just please do. So like I said, if you did not get a chance to send Chapter 7 homework to me, please do so, because again, I try to get you guys some feedback back. to you so you guys understand what it is that I think you're doing correctly. You're doing great. A lot of you guys did fantastic on this. And a couple of you guys just need to add a few things. You did fine with trying to find calculations, but again, I want to see those 3 parts so you can see it. So the first part, let's see if I can do this correctly. So okay, so the first part we want to look at is, let me zoom in a little bit so I can see, is how do we anticipate this? Well, first of all, again, we're just looking for the probability that X is less than 100. We're going to let X be the time it takes to get one car through the Wendy's drive-thru. That's an X. That's a randomly selected car. Okay? So X is going to vary from car to car. That's why we call X a random variable, going back to chapter 6. What kind of a random variable is it? Well, this is a continuous random variable because time can be measured in seconds, but it can also be decimals involved too. So we wouldn't want to use a discrete random variable with this because, again, there's just too many possibilities for this. So this is why this is a continuous. Now, we can only determine probability then because we know that this is a normal distribution. We have a procedure for this. And then we can just simply standardize it, 1, which is what I did next. We took that 100 and I changed it to a z-score. Do you guys remember how to change a value to a z-score? So where did the negative 1.32 come from? Think about that for a second. How did I get negative 1.32? Okay, so if you thought about it, remember, I'm taking this value 100, I'm going to subtract it from the mean, which is 138.5. So we know right away that I'm going to get a negative value because 100 is below the mean. Below the mean will give me a negative z-score. Above the mean will give me a positive z-score, and exactly at the mean will be 0. Okay? So we know we got this is 100. So if I change it to a z-value of negative 1.32, now I can go to my table. If anybody wants me to, I can show you on the table again one more time how to find this. But if you go to negative 1.32, you're going to get a value of.
Do you mind showing us the table?
I won't. No, not at all. That's why I asked. We can show you that real quick. So where does negative 1.32? How do we change that back to a percentage? So I'll just go to my Z table. This is like the one that's it's in your back of your book. This is table 5. Okay. And half of it, again, I think you guys just have one complete sheet that has negatives on top and goes all the way to positives on the bottom. So I'm going to show you this real quick. So we need negative 1.32. So on the left-hand side is where my negatives are, okay? So we can see that right there. There's negative 1.3, and then I'm going to go over 0, 1, and 2. And if we can see that, I'll zoom in a little bit. You can see the value right there. Nope, it won't let me zoom in on it. Okay. I thought I was going to be able to highlight it, but right there you can see it's 0.0934. So again, negative 1.3, negative 1.30, negative 1.31, negative 1.32. It's right there. So again, now the reason why I didn't have to change anything is because this already finds me percentages to the left or less than the given Z value that I had. So less than, I read straight from the table, I'm going to get 0.0934. Cool with that? You guys got any questions? So 1, I changed 100 to a Z-score. My Z-score was negative 1.32 standard deviations below the mean. 2, I go to the table. I've standardized this. I've taken a normal distribution and I've made the mean 0 and I made the standard deviation 1. Okay, and then 3, I just read the value that matches up with negative 1.32. Okay, Rachel, don't hurt yourself. Please don't rack while you're doing this class. If anybody can't see, Rachel's in her car. She's driving while she is listening to this wonderful session. Okay, please don't hurt yourself. Okay, cool. So let me go back.
I genuinely almost ran into a fan just to give you the finger.
Okay, thank you. Appreciate it.
You're welcome, always.
So this is 0.9334. Now, don't forget, now, again, this is first step. First step is to state the problem. That's where I changed it to the symbols. Probability that X is less than 100. Second step is we calculate. A lot of you guys in the homework had just simply the calculation. That's excellent. So if you got the calculation down, that's really good. But again, I also want to see this third step involved too, and this is where you're going to actually interpret this value. And again, it's merely nothing more than just simply restating the problem. You're just simply restating the problem. So the probability, oh, I left the word out. The probability that a randomly selected car will get through Wendy's drive-through in less than 100 seconds is 9.34%. And that's our interpretation. So make sure, again, you have all three parts in there. One, state the problem so I know exactly what you're looking for, because if you get a wrong calculation, I won't know why you got a wrong calculation. So I want to make sure that you're setting it up, you know what you're looking for, okay? And then finally, again, this is an analysis class. It's not a raw calculations. A lot of the stuff you can do in StatCrunch, and you can get it that way. I want to make sure you know what this number means. And does it make sense? Yeah, go ahead.
This is Latanya. So when we use StatCrunch to do the calculations, we have to find the z-score, or we could just put in the information that we have. Because I know
You
when
can
I
use
did the
either one. Either one. I'll show you real quick how to do it in your StatCrunch. Okay.
I know how to do it. You don't have to. I would just say, because I think what one of the comments when I did the homework, you said something about I didn't find the z-score, and I did it in StatCrunch, so I didn't know I had to.
Oh no, I'm sorry. Then I'll go back and look and see what I did there. But if you don't have, if you're using StatCrunch, then yeah, no, you don't have to.
Oh, okay.
Okay, so let me show you real quick StatCrunch. So if you're using StatCrunch, can you guys see my StatCrunch? So I'm going to a normal calculator. I've put in 138.5, that's the mean time, and my standard deviation is 29. And we wanted to find the probability that a car will take less than 100 seconds. And if I do that, we can see that I do get a mean of, or I get a time of, a percentage of 0.0921, which is about 9.2%, which is a little different than the one we got using z-scores. And like I said, you're going to get a little bit of a difference. That's why I like to go a few percentage points. So I think we always go 4 decimal points when doing percentage. So 0.0921 here. And if you're using z-scores, again, you're rounding off the z-score a little bit. That's why your percentage is going to be a little different. But I like to use either one because I like to use this because you can see on the normal curve. Most of the time, it's going to take you about 139 seconds, which is right here. Okay. Less than 100 seconds doesn't happen too often. Definitely doesn't happen when I'm going through the drive-through, but it could. Okay. And you could say it happens about 9% of the time. Cool, questions. And you can do either one, but I still need to see the 3 steps. 1, show me the percentage, set up the problem, give me the calculation. If you're not doing z-scores, again, just put it into StatCrunch. You can do it that way. Like I said, if you want to change everything to z-scores, that's fine. Maybe.
How do we get 1.32?
How do we get negative 1.32? That's where you take your, hold on one second. Let me do this first. Negative 1.32. If you do it with z-scores, you're still going to get the same thing, 0.0934. And again, the reason why this is a little different is because I rounded off the z-score. I rounded off the z-score. Whereas if I did the other way, I did not. So let me show you again how we get that. Where do we get negative 1.32 from? Well, first of all, we had a 100, and we subtract that from the mean, which is 138.5. Okay, when we do that, that's a negative 38.5 seconds. So that's 38.5 seconds below the average. Well, how far away is that from the mean? That's where you got to divide by the standard deviation. And the standard deviation was 29 seconds. So when you do that, 100 minus 135, and again, if you're using a calculator, make sure you put that numerator in parentheses, or simply do the numerator first, hit enter, and then divide by 29. And you should get negative 1.32. Questions? And that's your z-score. This is the z-score for 100 seconds. I still didn't get my stylus yet. I ordered it through Amazon. Nothing's coming fast these days. So once again, you get my 5th grade handwriting, or 5th grade, 5-year-old handwriting. I think a 5th grader could probably draw better than I can with my finger. Cool? So that's where negative 1.32 comes from. And again, if you're changing it to z-scores, you always have your calculator right here, okay? If you're using StatCrunch, you gotta make sure you have access to StatCrunch, and then you can just put those values in the way that it was in there, okay? Cool? All right, so let's go back and see. Second question, make sure again, this is just review of chapter 7. But the reason why we're gonna do this is because this is gonna lead right into chapter 8. So what is the probability that a randomly selected car will spend more than 160 seconds in Wendy's drive-thru? And that, of course, is me when I'm at the drive-thru. It usually takes me a long time to get my food. So it's just me. So this is the same setup. In other words, we're just changing the value of x. Okay. In this case, we're changing it. So now we want to find the probability that our car is going to be more than 160 seconds. Again, I want to see that first step. You put it in symbols, tell me exactly what I'm looking for. What is the probability that a randomly selected car? That's x, that's the time. What's the probability? That's p. Now p can stand for probability. It could stand for proportion, or it could stand for percentile. What percentile would 160 seconds be at? So you can interpret this final number 3 different ways. It's either a proportion, a percentile, or a probability. Okay? So we took the 160 and we can change that to a z-score. So again, with this one, we're going to take 160 minus 138.5 divided by 29. Okay, now 160 minus 138.5 is obviously positive. So now you know you're going to have a positive z-score, not a negative z-score. And when you do that, you're going to get 0.74. So 160 seconds is 0.74 standard deviations above the mean. 0.74 standard deviations above the mean. And Rachel's out of her car. Fantastic. Congratulations, Rachel.
I'm sorry, what? Are you talking shit?
No, I just said you're out of your car. That's good.
Oh,
You're not
Sorry,
driving
I
anymore.
just heard my name.
Oh, wow.
So for this one, why did we do 1 minus p, but the one before we didn't?
Okay, we'll show you the 1 minus in a second. Okay, remember our probability our table only finds area to the left or less than. It does not find greater than. So notice how I changed the symbol. Okay, if it's greater than, remember my table only finds area to the left. So if you want to find area to the right, you have to find the area to the left and subtract that from 1. It'll be the complement. So the area to the right is the complement of the area to the left. And your table only finds area to the left. So from here over that way.
So if it's less than, we just do -1 in
Yeah.
front of it.
If it's less than, you don't have to change anything. You can just simply read the percentage that's off of there. Okay. So the probability that you're going to spend less than 160 seconds is going to be here. So 77% of the time, you're going to spend less than 160 seconds. If you subtract that from 1, that means you're going to spend more than 160 seconds about 23% of the time, 22.96%. Does that make sense?
No.
And again, we'll go, does it make sense?
Yeah.
Okay, so first, tell me where you're lost.
So when you enter, I guess where you got the I, is that what you enter in StatCrunch, right?
I can, this is not StatCrunch. This is using the table in Z-scores. I'll show you in a minute how to do this in StatCrunch. Okay?
All right.
So if you're using the table and you're changing everything, if you're going to use the table, you got to change all the values to Z-scores. Because I do not have a table specifically for Wendy's drive-through times. Okay, I only have a table of standardized numbers. So what we do is we take our numbers of our times and we standardize them by changing them to Z-scores. And now I can use this table to find those values. Okay?
Mm-hmm.
So I'll go back and I'll show you what that looks like in our Z table.
Did you say fuck me?
Nope. If it sounded like that, I apologize, but it did not. Okay. So 0.74, and once again, right here, that's where 0.7 is, and I'm going to count over. This is 0.70, this is 0.71, this is 0.72, this is 0.73, and this is 0.74. And what's the value that matches up with 0.74? Is 77.04%, or 0.7704. That's where I got that value. So I took the Z-score of 0.74, changed it to my percentage, which is 77.04, or 0.7704. Okay,
I'm not
now remember.
understanding.
Go ahead.
I'm sorry.
That's like I get how you got the Z-score, but I'm still lost why we're doing 1 minus.
One
I don't
minus.
get why we got the Z-score of 7704.
Well, our Z-score is not 7704. Our Z-score was 0.74. Okay, so in other words, 160 seconds is 0.74 standard deviations above the mean. Okay, so let me go back to this real quick. So we want to find the probability that your car is going to spend more than 160 seconds in the drive-thru. So what did I do with 160 seconds? What's the first thing that I did? I found out how many standard deviations is 160 above our mean. And what's our mean again?
138.5.
That's the average. So obviously 160 seconds, is that more than the mean or less than the mean?
More?
More. Well, how much more?
A lot.
Well, how many standard deviations above the mean is that? Got your Z-score.
174.
So you are almost 1 standard deviation above the mean, but not quite. Okay? So let me see again. So let me go back to my whiteboard.
I get how you got the 7704. I just don't understand where the 2296 came from. Like, did you get the Z-score of 7704 to get 2204?
So here's what we're doing, okay? So let me draw this real quick. So here's our normal distribution. 138.5 is right here, okay? So let's say 160 is about here. We want to find this area right here to the right. We want to find out what percentage of cars spend more than 160 seconds in the drive-through. That sound good so far?
Mm-hmm.
Nothing blowing you out of the water yet. Okay. Now, I want to find that percentage using this table. Okay. But unfortunately, my table does not tell me the average wait time of the Wendy's drive-through. This only tells me standardized scores. So these are my X values right here. I'm going to change these to a Z value, which is a standard score. So I'm going to use 0 as my mean. And I want to find out what this is right there. What is 160 as a Z score? And again, how do you change 160 to a Z score? Well, you subtract the mean. And divide it by 29. Okay?
Mm-hmm.
And if we do that, we find out that that is point, oh, let me just erase. This is 0.74. Okay?
Okay.
So what all we did was take 160 and I changed it from an X value to a Z value. Does everybody see that? Now, why did I do that? Because my table can find Z values. My table cannot find Wendy's drive-through times. So it's not going to find 160 seconds. It's going to find 0.74 standard deviations above the mean. Now, unfortunately, how do I change the color on this? Where's the color? Oh, look at that. Okay. Unfortunately, your table only finds area to the left. It doesn't find area to the right. So what we're going to do is we're going to find that percentage first using our Z table. Okay. So we're going to find the area to the left and subtract it from 1. And when we subtract it from 1, we're actually going to find the area on the right. So we're going to take 1 minus that percentage, and that's going to equal that percentage. That's why we did the 1 minus. Cool?
Mm-hmm.
And we only do that if we're looking for area to the right of the curve.
Okay, so I lost my question. Never mind.
That's okay. That's okay. If you think about it, come back to me. All right?
So we doing it if it's a positive Z score?
I get what he's saying. I just don't understand why we subtracted 1 twice and we didn't do that in the other one. I kind of see why.
Well, this one up here at the top, look at part A again. Part A was already less than. So we didn't have to subtract from 1 because this area is already to the left. That's less than. Okay? It all depends on what your symbol is, whether or not you're going to change it. This one is greater than, so that's area to the right. Okay?
To the right, what?
To the right of our mean, or to the right of whatever value we're looking for. So again, to the right. Okay, so let's do this real quick. This is my normal curve. Okay, here's 138.5. You still with me?
Yeah.
Okay, here I was looking for 100. And again, I'm trying to find the area that's less than 100 seconds. So less than 100 seconds would be area to the left of 100. So that's what I mean by to the left. To the left of 100 would be all times that are what? Less than 100 seconds. Okay? Now, the reason why I didn't have to subtract from 1 is that's what this table, the table 5 tells me. My table tells me area to the left. Okay? Now, down here is a little different, right? Here is 138.5. But for this one, I wanted to find 160, and I wanted to find the area to the right of that. What cars spend more than 160 seconds. More than would be all of the times that are more than 160 seconds or to the right of 160 seconds. Our table does not find area to the right, it only finds area to the left. Now, if you're using StatCrunch, you can use either one. So let me show you again in StatCrunch. If you're a little confused with the z-scores, maybe you can just use StatCrunch if you're having problems with that, okay?
So
So you should-
anytime it's on the right side, we're gonna do 1 minus.
Every time it's on the right side, it's gonna be 1 minus, correct. Okay? So for this one, I'm going to find area to the right, but you can find the area to the right by just switching the symbol on this on. In StatCrunch, you can find area to the right. Okay? So let me go back to what this was before. It was 138.5, standard deviation of 29, and we want to be more than 160 seconds. And that's it.
Okay, it makes sense.
That makes more sense or less sense?
I think it's just easier to do it as TechCrunch.
Yeah, well, like I said, then you can use either one. Yeah, I accept either
So
one.
does
But
it
again,
matter?
the reason why I show you both methods is because not everybody has access to StatCrunch all the time. So you need another method, you need a backup plan. This is your backup plan if you don't have StatCrunch. But you can always use StatCrunch. Yeah, it is a little more efficient. Okay. But if you're not using StatCrunch, if you're using z-scores, you have to change everything so that you can use this nice paper pen thing and no technology needed.
So if we're using a StatCrunch, we can just write whatever on like a test or something. Like
But I still want to see the
Hey,
stats.
don't hit the show.
I want to make sure that you see it. So again, so let me go back to what I need to see on the test. Okay. So in other words, if you're using StatCrunch, you still have to show me this part, but you don't have to show me this part. You can just go right to here. Okay. There's step 1. Step 2 is you calculated it. Okay. And then I still need an interpretation.
so just the sentence after that.
Yeah, you still need to interpret your value back. So again, here, let me erase this one. So the probability that a randomly selected car will spend more than 160 seconds is 22.96%. Okay. So this is 1. I need to see this.
We only see StatCrunch.
Oh, you only see StatCrunch? Hold on. I didn't change it back.
No.
There we go. How about that?
All right.
Sorry. So I'm doing things that you couldn't see. Okay. So step 1, one more time. What do I need to see? This is step 1. Step 1 is you took your problem and you translated it. So you're stating the problem. That's stating the problem. I want to find the probability that my car is going to spend more than 160 seconds. This is step 2. This is the calculation. You can change it to z-scores and use a table, and you can find me that number. And then step 3 is the interpretation. Okay? If you're using StatCrunch, you don't need to do this part. You can go right to here. So there's step 1, probability that x is greater than 160. Step 2, 0.2296 is your calculation. StatCrunch or using a table. And again, I had about 25% of you guys use the table for this when I saw the homework. A lot of you guys were using the table. That's fine. I like to use the table too. It just takes an extra step to change everything to z-scores. Now, if you were in class, I would also have you guys draw a table, but I know that's going to be hard to do if you're typing out answers. So I like to have you guys sketch a curve for me. So if we were face-to-face, I would have you do the curve so you can show me exactly what it is you are looking for. In other words, this is your area of interest. What area am I looking for? Because I want you to think of percentage as an area. How much of the normal curve is shaded in? Well, 22.96% of the curve is shaded in. That's our probability. Cool?
Mm-hmm.
Questions? All right, I'll breeze through this last one so we can get to the next section. But this is basically, again, and everything that we did on the homework, everything that's right here, these are going to be your assessment problems. Okay? Nothing more, nothing less. Okay, cool. So let me zoom up a little bit. What proportion of cars spend between 2 and 3 minutes? And I'll put this one up on the screen real quick, what this looks like. So for this one, again, this says between 2 and 3 minutes. Now be careful with this because all of our times were in seconds. So you wouldn't want to put 2 and 3 in with the X because again, you've already made sure that your mean and standard deviation are in seconds, not in minutes. So this one was a little tricky in that I needed to change that to 120 seconds and I needed to change that to 180 seconds. So what percentage of cars, what proportion of cars spend between 2 and 3 minutes? Okay, we can see that it's a pretty big proportion, right? 120 seconds is 0.64 standard deviations below the mean. Okay.
So when it's between, it's a less than?
Well, it's between. So notice how X is between these two numbers. So X has to be greater than 120, but less than 180. That's called a compound inequality. You see how that's set up when I'm doing between?
Yeah.
That's
Okay.
called a compound inequality. So I needed to find two z-scores with this. I found one for negative 0.64. Okay, so if I take 120 minus 138.5, that's going to give me a negative value. If I take 180 and subtract 138.5, I'm going to get a positive value. Okay, so 120 seconds is 0.64 standard deviations below the mean, and 180 seconds is 1.43 standard deviations above the mean. Now, where these two values come from? So where'd these two values come from? Well, they come from the table. So the 0.9236 came from the 1.4. I needed to find the bigger number. And the 0.2611 came from this z-score. I'm finding the area in between, so I just simply subtract those values. Okay?
Mhm.
And then, of course, don't forget, you also need an interpretation. This is your interpretation. 66.25% of all cars spend between 2 and 3 minutes in the drive-thru. So let me show you what this looks like in StatCrunch. For this one, you have to actually hit the between button. And remember, down here, I'm going to go between 120 and 180. And you can see you got about 0.66.2. So 66.2% of all cars will spend between 2 minutes, which is 120 seconds, and 3 minutes, which is 180 seconds. And again, you can use StatCrunch for this. If you don't want to change the z-scores, if you don't want to use the table, you do have access to StatCrunch for the test. That's why I'm showing you two methods. Cool? And the only one we didn't practice, and I'll make sure that I'll throw a practice problem, is to make sure you can go backwards. If I give you a percentage, can you work backwards to find a raw number? I'll make sure that that goes up there as well. Let me give you a quick example. Let's see, let's go back to standard. Let's suppose I ask you the question like, what is the 30th percentile for wait times at Wendy's? What would be the 30th percentile for wait times? Well, if I ask you, if I give you a percentage of 30%, that means instead of, I'm going to put less than in, percentile is always less than. Now, instead of putting in a number down here, I'm actually going to put a percentage here. So I can put 0.30, that represents the 30th percentile. And if I hit compute, it'll say 123 seconds. So the 30th percentile for wait times at Wendy's would be 123 seconds. Now, in this case, your answer is not going to be a percentage. Your answer is going to be a time. So that 123 is going to be time, not a percentage. And I'll make sure I'll post another example up there in Blackboard so you can see that. Questions? Okay, cool. All right, here's what we're going to do tonight. We're going to talk with sampling distributions. This is chapter 8. This is day 25 of the Corona takeover, in case you guys are keeping score at home. Okay, so let's talk about it real quick. We're going to start talking about what is a sampling distribution. We're going to talk about that. What is a sampling distribution? And then we're going to be able to describe the distribution of a sample mean in a normal population. We're also going to be able to describe a distribution of a sample mean in a non-normal population. So let's talk about a little bit what a sampling distribution is. Okay? So we all know what a population distribution is. A population distribution is the distribution of all things that are in a population. So for example, we talked about Wendy's wait times. That would be a population distribution. That'd be all the cars that wait in Wendy's line. We took a look at all their times and we formed a distribution and we took a look at the entire population. But let's suppose I don't want to look at the entire population. I only want to look at a sample of the population. And why would I want to do that? Because it's easier to look at a sample or have access to a sample than it is to an entire population sometimes. So we're going to take a look at not the entire population, but just a sample of the population, and we're going to describe that. So what is this? So we know that statistics are numbers that describe a sample. Parameters are numbers that describe a population. So I want you to focus a little bit on statistics tonight. We're not looking at the entire parameter, we're only looking at a sample. Okay, so statistics such as X bar. What does X bar stand for again? Give you guys a second to think about it. What does X bar stand for? I don't have my chat up online, or I'd have you guys chat that for me. I suppose I could put that up there. Yeah, that's a sample mean, okay? So in chapter, we're going to focus on the shape, center, and spread of statistics, such as X bar. So we're not looking at the entire population. We're going to look at the shape, center, and spread of a statistic. Or not just one, but we'll look at many. Okay? A sampling distribution, that's what this chapter is. It's on sampling distributions, not population distributions, but a sampling distributions. And I'm going to show you what those look like. Okay? We're going to go to StatCrunch, and we have an app for that. Okay? A sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. Let's suppose, again, we're talking about our Wendy's drive-thru. Okay, we took a look at all the cars. Let's suppose I just take a sample of 5 cars, and I find out how long was the wait time for those 5 cars. And then I took the average time by simply adding up all of their times and dividing by 5. And when I do that, I'm going to get 1 X bar of size 5. I could keep doing that. In other words, I can take another sample of size 5 and then another sample of size 5, and I could keep doing this until I take all possible values of size 5. That would be a sampling distribution. So one more time. A sampling distribution of a sample mean is X bar, is the probability distribution of all possible values of the random variable. All possible values of the random variable X bar. So what does that mean? In other words, again, think back to the Wendy's drive-thru. Let's suppose I take one sample of size 5, and then I take another sample of size 5, and I keep doing this over and over and over again. I keep taking many, many, many samples of size 5, and I add up all their times, and I divide by 5. So I'm not looking at just one X bar, I'm looking at all of them. All possible X bars from a population, okay? Now again, so there's a third thing that we're gonna need. Not only do we need to know where the mean and standard deviation of our population, but we also need to know what the sample size is. So this is our parameter, this is our parameter, and we're gonna add one thing to that tonight. We're gonna make sure we know that we are in size 10. So size n, mean, and standard deviation. So it's going to look kind of similar to what we did in chapter 7, but we're going to add one more element to it, and that is, well, a sample size of little n. Okay, so how do we find a sampling distribution? So here's what we do. Step 1, we're going to take a simple random sample of size n. So I'm going to take 5 cars at random. I'm going to find out how long did they wait in line. I'm going to take all their times, add them up, and divide by 5. Okay? I'm going to find that that's called the sample mean. Step 3, assuming that we are sampling from a finite population, we're going to repeat steps 1 and 2. That's it. We're simply going to repeat step 1 and 2 all over again until we have all distinct simple random samples of size n have been attained. Okay? Now, you might be asking yourself, well, how many are there? How many possible samples could I take from a finite population? All depends on how big the population is. In many cases, you are never going to be able to look at all of them. We're only going to look at a partial sampling distribution because there's simply sometimes just too many samples to look through. But we have enough that we can actually figure out what that is, okay? So let me give you guys an example. We'll get into this. We're going to look at weights of pennies, okay? Weights of pennies that were minted after 1982. We want to look at the weight of a penny. So weights of pennies, now again, not every penny is going to weigh the same because again, it's impossible to get every penny to weigh exactly the same because there's going to be some variability. We know that there's variability in everything. How much variability is there? Well, we can see that in this, we have a population that has a mean of 2.46 grams and a standard deviation of 0.02 grams. Now again, we know the center and we know the spread. What we don't know is the shape. So for right now, I'm going to assume that the shape is normal. It may not be, but for right now, we'll just assume that it is normal because again, I can show you what that's going to look like. Okay, so let's take a look at what that population looks like and let's just assume for a moment that it is going to be normal. Okay. So let's go back to my options. We'll show you what this looks like. Hold on. Here we go. Okay, so let's show you what this looks like. Can everybody see this up on the screen now? I got a population at the top. Okay. Population at the top, and I'm showing you real quickly that my population has a mean of 2.4. So that's the weight of an average penny is 2.4 grams. The standard deviation is 0.02 grams. So we can take a look at that up here on the screen, okay? We can see that most of the time that I'm going to fall within this blue range right here, this blue line. That's one standard deviation above and one standard deviation below the mean. So most of my pennies are going to weigh around 2.4 grams, but there's going to be a little bit of variability involved. Okay, so at the top is my population distribution. At the bottom, down here, we are going to form a sampling distribution. So at the top, population. At the bottom, sampling distribution. But there's nothing down here yet. Why is there nothing down here yet? Because we haven't taken any samples. We're going to start with a sample of size 5. So over here, I'm going to take a sample of size 5, and I'm going to do this one time to show you what it's doing, what this simulation is doing. So I'm going to take 5 pennies at random from 1982 on. So I have taken 5 pennies, and I've weighed all 5 pennies, added them all up, and divided by 5. And I got a mean of exactly 2.4, which is right there. So all 5 of these pennies, I added up, and I got exactly the mean of 2.4. Okay? I'm going to take another sample. This one, I got a sample of 2.3968. We can see that it's awfully close to 2.4. So notice again, look at my variability up here. So each individual penny has quite a bit of variability, but my sampling distribution right now, not so much. Let's see if that continues. I'm going to do it again. Take another sample of size 5. Take another sample of size 5. And we can see that on the bottom now, what are we forming at the bottom? This is called a sampling distribution. So right now, what I'm looking at is many samples of size 5. Well, not a lot. I've only taken 7. So how many samples of size 5 can I take from a population of pennies? Well, a boatload. I can take a lot of samples of size 5. So let's repeat this 5 times. Let's go a little faster. So what I'm doing now is I'm going to take another 5 samples, and we can see how my sampling distribution is beginning to form. All I'm doing is taking 5 pennies at random, weighing all 5 pennies, and then finding the average weight of those 5 pennies. I'm not finding the average of the entire population. I already know what it is. The average of the population is 2.4 grams. What is the average of all my samples? Well, they vary. Sometimes they're a little more than 2.4, sometimes they're a little less than 2.4, but we can see how this is beginning to form together. So what I want you to do, first of all, is look at my sample of size 12. What is the mean of all of my sample means? The mean of all of my sample means is the same, or almost the same, as my population mean. So once again, the mean of all my sample means, which is right here at the bottom, if I can get it to highlight just on that. The mean of all of my samples is the same as the mean of the population. Okay, so I'm going to do this 1,000 times now, and this is actually going to go much faster. I'm going to take 1,000 more samples of size 5, and let's take a look at our sampling distribution. Maybe, there we go. Take a look. So boom, now how many samples of size 5 do I have? I have 1,012. What do we notice a little bit now? I want you to compare the population distribution on top with the sampling distribution on the bottom. What is the same about both these distributions? Well, obviously the mean. The mean of the population distribution is the same as the mean of my sampling distribution. Again, the sampling distribution is in green. The population distribution is in gray. I'm going to take another sample of size 1,000, and another, and another, and another. So right now I've got 5,000 samples of size 5, and we can see pretty clearly that the mean of all of my samples is the same as the mean of my population. What's different about these two graphs now, and this is very important, this is the most important concept of the evening, is I want you to notice what is the big difference between the gray distribution and the green distribution. Take a second real quick. Tell me what the difference is between the two and see if you have a number that can help justify the difference.
Is it the standard deviations?
Perfect. What do you notice about the standard deviation of the green one?
It's 0.008, and the first one, the population one, is 0.02.
Correct. So we can see that the standard deviation of the green is considerably less than the standard deviation of the gray. Cool? So let's make sure we understand. The distribution, right now, what do you notice about the shape of the population? The shape of the population is bell-shaped or approximately normal. What is the shape of the green? Well, it's also approximately normal. So we got similar shapes. We also have the same center. The center of the grain or of the population is the same as the center of the sampling distribution. Now, what's our sample size? Our sample size was size 5. What if we increased the sample size? What if we no longer took a sample of 5 pennies? What if we took a sample of size 20 pennies? So I'm going to reset this, and we're going to take a sample not of 5 pennies. We're going to take a sample of 20 pennies, and we're going to take the mean of 20 pennies. So I'm going to do that one time. So I have taken 20 pennies, I've added up all their weights and divided by 20, and I got a sample mean of 2.399, which is awfully close to 2.4. Okay, I'm going to take another sample of size 20. Maybe. I'm going to take another sample, and another sample, and another sample. And now what are we forming down below? We are forming a new sampling distribution down below. This one has the same population mean and the same population standard deviation, but now we are taking a larger sample size. The sample size we're taking down below is now sample of size 20. I'm going to repeat this a couple of times and we can see how my sampling distribution is forming down below. Okay, we can see how the sampling distribution is beginning to take shape, take form. I'm going to do this 1,000 times now and really speed this up. So now I've taken a sample of size 20. Now, what do you notice about this population distribution, which hasn't changed, and now this sampling distribution, no longer of size 5, now we're taking a samples of size 20. So what is the difference between this population distribution, this sampling distribution? What do you notice? The bigger the sample, what happened to our variability? Well, with size 5, we had a variability of about 0.0088. When we increased our sample from 5 to 20, our variability went down to 0.0045. Okay, so what can we take away from this? Well, if I have a population distribution that I know is normal, and I know it has a parameters of mu and sigma, or I have a mean and standard deviation, that my sampling distribution is going to be very similar in that it's going to be the same shape, it's going to have the same center, but it's going to have different spreads. So what can we take away from this? The bigger the sample, the less variability that we're going to have. So what if I did a sample of size 200? Now I'm going to go from, again, so what do you think is going to happen in this case? My battery's running low. While you guys think about that, I got to go get something to plug in my computer. here we go. Okay, all right, now I'm plugged in. The sample size of 200, what's going to happen? Well, I'm going to do this a few thousand times, and we can see that our sampling distribution got really skinny. In other words, samples of size 200 are going to give me really small standard deviation. In other words, there is very little spread if I'm doing samples of size 200. So once again, same mean, 2.4, the mean of my sampling distribution, 2.4. This one had a standard deviation of 0.02. This one has a lot less standard deviation. So the bigger the sample, the less variability. Bigger the sample, the less variability. And I'll put that up there in a second. So here's what we did, okay? So let me go back to the PowerPoint, okay? So the weight of pennies after 1982 are approximately normally distributed. That's important, with a mean of 2.46 and a standard deviation of 0.02.
We can't see.
Oh, hold on a second. I forgot to share it. Thank you. I gotta make sure I do that. So even if I change it on my computer, it doesn't mean I switched it on yours. So thank you for bringing that up. Okay. So we're back at the PowerPoint. Okay, so let's see what this looks like. So again, one more time, I'm going to walk you through now again. Since we saw a look at what that's going to look like. So here's one sample of size 5. Okay. If we add them all up and divide by 5, we're going to get a sample mean of 2.44. That is one sample. Now let's say I do that a whole bunch of times. So what are all those numbers? Those are all sample means for samples of size 5. I can do it a couple hundred times. So I've taken 200 samples. Those are my 200 samples of size 5. And the sample mean is 2.46, which is the same as the population mean. But the standard deviation of the sample means is 0.0086, which is smaller than the standard deviation of the population. We're going to show you what that looks like as a histogram. So those are 200 samples of size 5 pennies. We've taken all the pennies, weighed them, added them together, and divided by 5. And every single one of those frequencies represents a sample of size 5. So what role does n, the sample size, play in the standard deviation? Okay, so this is big concept number 1. This is pretty much what we need to know for tonight. As the size of the sample increases, the standard deviation of the distribution of the sample mean is going to decrease. And again, we're not looking necessarily at the population distribution. We are looking at what's called a sampling distribution. This is a distribution of many samples, in this case, sample means. Okay? Now let's suppose, again, this is where we're going to increase from a size 5 to a size 20. So what happens if we go from 5 to 20? So I'm going to look at 200 samples. Now, same population, but this time I'm going to increase my sample size from 5 to 20. We already know what's going to happen. The standard deviation went from 0.0086 to 0.0045, which means it got basically cut in half. Okay, so here's what you need for tonight. These are the parameters that we're going to talk about. Let's suppose we want to find the mean and standard deviation of a sampling distribution. So the first thing you need to remember is that the mean of a sampling mean is going to be the same as the population mean. Okay, go back real quick. I just wanted to erase this. Okay. Dun, 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 dun. The mean, this is the first part. The mean of X bar is the same as the mean of the population. So The mean of all my sample means is the same as the mean of the population. Now, the standard deviation, this is where you're going to have to do your one calculation. To find the standard deviation of your sample mean, you're going to take the standard deviation of the population and divide it by the square root of n. The square root of n. This is called the standard deviation of the sampling distribution. So we're still going to use sigma, but we're going to put a little x bar next to it. So this is the standard deviation of my sample means, not the standard deviation of my population.
So, for example, would n be like before we were doing that? We were going to do 5 pennies. So would n be 5?
Cool. Yep.
Okay.
So if our population standard deviation was 0.2, you would have to divide by the square root of 5 to find the standard deviation of the sampling distribution. And if we had a sample of size 20, we would take the 0.02 and divide by the square root of 20. So this got me about 0.088. And this got me about 0.0045. So we can see the reason why that the standard deviation gets smaller is because n is located in the denominator. So when you increase the size of n, the overall fraction becomes smaller and smaller. Again, when the denominator gets bigger, the overall fraction gets smaller. It's kind of like an inverse relationship. Okay, so let's show you what that looks like. I'm going to give you an example. Well, first of all, let's talk about the shape. So we know what the center and spread is. So let me go back. This is my center. This is the center. Oh, let's go back. This is the center, and this is the spread of a sampling distribution. That's a mean and a standard deviation. We're going to use mu again. We're going to use sigma again, but we're going to put a little subset of x bar there to let me know that this is the mean and standard deviation of a sample mean. Okay? Now, we have to talk about the shape. The shape is also important. Remember, we can only find the shape of a normal distribution or find probabilities. So this is the first part. The shape of a sampling distribution of x bar if x is normal. So if my population is normal, then the sample mean x bar is also going to be normal distributed. One more time. If my random variable x, that's the population. If x is normally distributed, that means my sampling distribution is also going to be normally distributed. No matter what the sample size is. Okay? Cool beans. So let me take a look at an example. All right. So the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 and a standard deviation of 0.02. What is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? All right, that's a big mouthful. So we're still finding the same thing. So let's make sure we understand what we're doing. Okay. We're finding probability with a normal distribution. The population is normal, so we know that the sampling distribution is also going to be normal. So we can use a normal distribution. We can use a normal calculator in StatCrunch, or we can simply use a z-score with this as well. This one's a little different in that we have an n now. N is size 10. Okay? So let's see how this is set up. let's take a look at the solution for this. The first part is, let's make sure we know that X bar is normally distributed. If it's normally distributed, we need the parameters. So what is the center? The center is also going to be 2.46 because the center is going to be the same as the population. But however, what happens to our standard deviation? It's going to go down. The reason why it's going to go down is because sampling distributions have less variability than populations do. When we increase the sample size, the variability decreases. So we're going to go from 0.02 down to 0.0063. And how do we get that? We divided by the square root of n. Okay? This was my population standard deviation divided by the square root of n. The standard deviation of the population was 0.02, and our sample size was 10. So we're going to do the same thing, okay? So what do we do next? We can change that to a z-score. So how many standard deviations above the mean is 2.465? Well, this time we're not going to divide by 0.02, we're going to divide by 0.0063. So the only thing that changes between the problems we did last night or last week and the problems we did at the beginning of classes, the only thing we have to do is we have to change our standard deviation because we are dealing with samples now, okay? And then if we do that, we can do it the same way. So we want to find the probability that z is greater than 0.79. Now, why do I subtract from 1? Well, that's because, again, I'm finding area to the right. Anytime I want to find area to the right, I first have to find the area to the left if I'm using a table. Okay? Now, we can also do this in StatCrunch. We're not going to do anything different. Okay, so let me take this out of here. Going to go back to my normal calculator. This time again, I'm going to use the same mean, 2.46, but this time my standard deviation was 0.0063. And I want to find the proportion of all samples of size 10 that are more than 2.465. I'm going to get about 21.4%. So the only thing different is right here, the standard deviation is going to change. We're still using a normal calculator. If we have a normal distribution, we're going to have the same mean as our population, but our standard deviation is going to decrease. Well, how much is it going to decrease? It all depends on how big the sample is. The bigger the sample, the smaller the standard deviation. So that's what that would look like in StatCrunch. So one more time. Standard deviation's the same. Standard deviation, all we did was change it to 0.0063. Okay? Any questions on that? Cool. All right, so we got to look at one more situation, and then we're done for the night. Let's suppose we talk about a population distribution that is not normal. I'm going to look at the frequency of rolling a die. This is what's called a uniform distribution, right? If I'm rolling a die and I want to find out how often the 1, 2, 3, 4, 5, 6 pops up. Well, since they're all equally likely to happen, this is what my distribution is going to look like. Notice again that my population distribution is not normal. See, I said right at the bottom. Not normal.
You're still in StatCrunch.
You're still in StatCrunch? Thank you. Go back to the thing. Guys are killing me. I'm killing me. All right, there we go. So let's erase that. Let's start over, take 2. So one more time, this is what this would look like in StatCrunch. Okay. Now we're going to look at population distribution again. So we want to look at when is the population distribution not normal? Because let's face it, a lot of our population distributions are not going to be normal. Okay, they just don't happen all that often. This is the table of histogram for a probability distribution for rolling a fair die. Notice that my population distribution is uniform. Uniform just simply means it makes this nice rectangle here. This is definitely not a normal distribution. So if I were to take the mean of all these numbers, I'm going to get a mean of 3.5 and a standard deviation of 1.708. Now, our distribution does not have to be normal to find a mean and a standard deviation. All distributions are going to have a mean and a standard deviation, even if the distribution is not normal. So we're always going to have a mean, we're always going to have a standard deviation. But the question is, will we always have a normal distribution? And the answer is no. So all we're going to do is what happens if we don't have a normal distribution, okay? So here's what I'm going to do. I'm going to take a sampling distribution. I'm going to take 200 simple random samples of size 4, which means I'm going to roll one die 4 times. I'm going to take those 4 values, add them up, and divide by 4, and I'm going to get myself a sample mean. So one more time, I'm going to roll the dice 4 times, add them all up, divide by 4, and I'm going to get a sample mean, okay? So for right now, I'm going to do a sample of size 4, and then I'm going to repeat for a sample of size 10 and a sample of size 30. So first of all, we're going to look at a sample of size 4. We want to find out what is our sampling distribution of X bar going to look like. Well, remember what the population distribution looked like. It looked like a uniform. It's just one big happy rectangle. I want to know is what is the sampling distribution going to look like? What is the shape? So everybody take a look real quick. This is my sampling distribution of sample of size 4. It's definitely not uniform, is it? It's actually becoming kind of bell-shaped. So that is 200 samples of size 4. This is 200 samples of size 10. Again, we're noticing that the shape is beginning to form what looks like a bell shape. And look what happens when n is 30. When n is 30, we almost have a perfectly symmetrical bell-shaped or approximately normal distribution. So even though our population distribution was not normal, the sampling distribution is normal. So that brings us to big concept number 2. Concept number 1 is the bigger the sample size, the less variability. Now, the second big concept also has to do with what happens when we increase our sample size. What happens to the shape? Okay, so here's our key points from this example. Now remember, the mean of a sampling distribution is equal to the mean of the parent population. So that's always easy. So whatever the mean of the population is, that's also the mean of the sampling distribution. The standard deviation is going to decrease when the sample size increases. And so our big concept is right here now. This is what we're looking. The shape of the distribution of a sample mean becomes normal as the sample size of n increases, regardless of the shape of the underlying population. And that's very important because once again, not all of our population distributions are going to be normal, but our sampling distributions are going to be normal as long as our sample size is big enough. Okay? This is what's called the central limit theorem, and I'm going to highlight that. The central limit theorem is just going to restate what we just did. Okay? So here's what I want you guys to make sure that you understand. This all has to do with the shape of my sampling distribution. And what we need to remember is regardless of the shape of the population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. Increases. So the next question you're probably thinking of is, well, how much does N need to be? How big does our sample size need to be before we know that our sampling distribution is going to be normal regardless of our population distribution? So here's what we're going to do. I'm going to put this little rule in here. So this is what you're going to use as your little cheat sheet for this chapter. So I want you to mark this as cheat sheet number 1. This is cheat sheet number 1. When we are doing a sampling distributions of a sample mean, and I'm going to give you guys a chance to write this down, or like I said, it's already posted to our Blackboard if you just want to look at it later. So this is our population distribution. We got 2 situations. What happens if the population is already normal? Okay. And what happens when our population is not normal, or we simply don't know what the population distribution is? Okay. So what happens if the population is normal? Well, this is the shape. The shape is also going to be normal regardless of the sample size. The mean of all the sample means is going to be the same as the mean of the population. That never changes. The standard deviation of the sample mean is going to be the standard deviation of the population divided by the square root of the sample size, which means as N increases, the standard deviation is going to decrease. Okay? That's if our distribution is normal. So if we have a population that is normal, the shape is going to be normal of the sample mean. The mean of the sampling distribution is the same as the mean in the population, but the standard deviation is going to decrease. It's going to become smaller as N becomes larger. The second situation is when the population is not normal, or we just simply don't know what the population distribution is. We don't know what the shape is, but we still have a mean. We have to be given a mean. We still have to be given a standard deviation. So what is the shape of our distribution then? Well, remember, we don't know what the shape of the distribution is unless N, and this is our rule, and I want you to do this, okay? Make sure you know this number. Little n has to be greater than 30. If little n is greater than 30, then our sampling distribution is going to become normal, regardless of what the population distribution is. Okay? And again, this is called the central limit theorem. This is by what's called the CLT. For those of you that have taken calculus, you also know that central limit theorem is a very, very big concept there, very similar concepts. Now, notice again, same mean, same standard deviation. So we're always going to use the same mean, always use the same standard deviation, but what we're doing is making sure that our shape is normal. So when you're looking at the problem, look to see what your population is. Is your population normal? If it is, then X bar is always normal. Look in your problem again. If X bar is not, if the population is not normal, you need to make sure that N is greater than 30. If it's not greater than 30, we can't do any calculations, because we can only do a calculation of a probability or a proportion or a percentile if our distribution is normal. That's the only calculator we have. We have a normal calculator. We have to make sure that our distribution is normal. Cool? We are wrapping this puppy up. So let me show you what that looks like. I'm going to give you an example, and then I got a couple examples in the thing that I've downloaded that you can look at as well. Suppose that the mean time for an oil change at a 10-minute oil change is 11.4 minutes with a standard deviation of 3.2 minutes. The population distribution is unknown. So I don't know what the shape of this population distribution is, but I know that the mean is 11.4 minutes. I know that the mean is 11.4 minutes and it has a standard deviation of 3.2 minutes. So I am not going to look at an individual car, and I'm not going to find out how long it took this car to get an oil change. I'm going to look at a sample of 35 cars. I'm going to take a random sample of 35 cars, and I'm going to look at what is I want you guys to be able to describe the sampling distribution of this random sample of 35 cars. Okay, so we want to be able to describe this distribution. So first of all, what is the shape of this distribution going to be? Well, the population distribution is unknown. But our sampling distribution is going to be known. We know that the sampling distribution is going to be normally distributed. Well, how is that? Because remember, we know by the central limit theorem. The central limit theorem tells us as long as n is greater than 30, our distribution of the sample mean is going to be normal, even though our population distribution is unknown. Our sampling distribution is going to be normal because n is greater than 30. Okay? What is the mean of our sampling distribution going to be? Well, all we have to do is look at this up here. The mean of the population is 11.4. So the mean of my sampling distribution is also going to be 11.4. Okay? Now, how much does each individual car vary from oil change to oil change? Each individual car varies by about 3 minutes. But if I'm looking at the sample mean of 35 cars, we know that's going to decrease. So how do we find the new standard deviation? I have to take 3.2 divided by the square root of 35. So my new standard deviation is going to be 0.5409. So one car will vary by 3.2 minutes. But 35 cars will only vary by about a half a minute. A lot less variability when you're looking at sample means. The bigger the sample, the less variability. So that's the first thing we need to do is find out, make sure again, our distribution is normal, the mean, and standard deviation. Once you find out that you're normal, you need your parameters now, your mean and standard deviation. Once you have those, this problem becomes exactly like the ones we did last week.
So I'm sorry, how did we determine that it was normally distributed?
Okay, this is called the central limit theorem. We'll go back real quick. The central limit theorem tells us if the population is not normal, our sampling distribution will be normal as long as our sample size is big enough. Let me show you what that looks like. Let me take a minute here real quick. I know we're pressing for time, but I'm going to make sure I got this. So let's take a look real quick. You guys see StatCrunch? Is StatCrunch back up?
Yes.
Okay. Let's go to sampling distribution. Let's suppose I have something that's skewed. I'm going to take a look at something that's skewed. Okay. Let's take a look at it real quick. Everybody see my distribution? It is definitely not normal, is it? Okay. This is a distribution that's skewed to the right. Now I'm going to take a sample of size 2. And I want you to tell me what my sampling distribution is going to look like. Is my sampling distribution in green, is this normal? Nope. It's also skewed to the right. So my population distribution is not normal, and my sampling distribution is also not normal. So I cannot do any calculations right now because I can only do calculations from a normal distribution. What happens if I increase this sample size a little bit? I'm going to increase it from 2 to 5. Now we can see that my distribution is still not quite normal. It's still a little skewed to the right, but it's a little more bell-shaped than the last one was. It's still skewed to the right, which means it's still not normal. Watch what happens though when I go to 30. 30 is the magic number. So every time I get a sample size of size 30, look what happens to my distribution. So even though my population distribution is definitely skewed to the right, my sampling distribution is now normal because I have a big enough sample size. I have a sample of size 30. So one more
Okay.
time. Go ahead.
So for the example, since the random sample was n equals 35 oil changes, that was greater than 30. So that's how we knew it was a normal distribution.
That's perfect.
Okay.
So one more time, let's repeat what you said. Who was that, Kayla?
Yes.
All right. See, I'm trying to recognize your voice. Okay. So how did we know that X bar is normal? Well, this came by the central limit theorem. The central limit theorem tells me if n is greater than 30, then X bar is going to be normal. Regardless of the fact that we didn't know the population distribution, we didn't know what the shape of the population distribution was. Okay? So as long as n is greater than 30. Now, what happens if n is not greater than 30? Well, we just simply can't make any calculations. Okay? Cool? Unless we check. We'll show you something later. What happens if n is less than 30? I'm not going to give you any that are less than 30. Okay? Unless the population distribution is already normal. Okay. So here's what this would look like, real quick. If you're using z-scores, I'm going to take 11 minus the mean. Our standard deviation is now 0.5409. That's going to give me a z-score of negative 0.74. So now I want to find the probability that z is less than negative 0.74, and that's going to give me about 23%. Okay? You can also do this in StatCrunch. So here's what it looks like in StatCrunch. Now, all I did here is I changed my mean. Now notice again, my mean is still 11.4. I changed the standard deviation to 0.5409. And again, that's the one calculation that you need to make before you put your data into StatCrunch. Do not put the standard deviation of the population in. You want to put the standard deviation of the sampling distribution in. It's always going to be less than the normal one. Okay? And that's it for 8.1. We're going to do 8.2 on Thursday. So we'll just stop there from 8.1. And again, let me make sure I got your highlights for tonight. Make sure you got this. This is our big summary right here. So we are not doing populations tonight. We are doing sampling distributions. A sampling distribution is a distribution of all samples of size n from a population. Now the population may be normal, the population may not be normal. That's what we got. Okay, so I'm going to give you one example problem before we head out. Or if you think you already got it, you can head out. I'll give you guys the assignment too. Okay. All right, so I'm going to go to the problems that I gave you earlier. Okay, so this is the one we looked at before when we first started the class. So I'm just going to scroll down a little bit. Can you guys see this? These are the example problems that are on your thing. So I'm going to start with this one real quick. So I think we did this before. We did something called the GRE. This was one of our last examples that we did from normal distribution. Okay. So let's take a look at this real quick. So let's take a look real quick. All right, so what is the probability that one randomly selected student will score above 147 on the quantitative portion of the GRE? All right, so let's look at this problem. So what do we know about this? Let's pick this apart. Make sure we got it. What do we know about the population distribution? Let's describe it. What do we know about the population distribution? Well, what do we know first? It comes from what? What kind of distribution is this? Approximately normal. If it's normal, that's our shape. What's our center? 150. What is our spread? 8.8. Normal distribution, 150. And our standard deviation is about 8.8. Okay? And again, hopefully I'll have my stylus soon and I won't look like a 5-year-old writing on this. So 158, that's it. That's our parameters. Okay? What's the question asking me? What is the probability that one randomly selected student scores above 147 on the quantitative portion of the GRE? Now, this is the same as last night. I didn't change anything. Okay? I want to find the probability that X is greater than 147. 147. So is this number going to be more than 50% or less than 50% based on our curve? Well, here's 150 over here. 147 is probably right around here. And I want to find the area to the right. So I want to find this percentage right there. Speed this up a little bit. I'm going to go to StatCrunch rather than go to this. So we're going to actually calculate this in StatCrunch. And let's go to Stat Calculator. Normal. 150. And 8.8. And we want to find the probability that somebody will score more than 147. 147, we're going to hit compute. What's our answer? Our answer is 0.6334. 0.6334. So it's equal to 0.6334. And we can say 63.34%, ... Don't forget, we want to put in our interpretation after that. So the probability that one student is going to score above 147 is about 63.34%. Cool? Nothing different. That's the same as what we did last week. That's the same as what we did at the beginning of class. Nothing different. Now we're going to add in the new element, which we did tonight. Everybody take a look at the second one. Okay. We're going to describe the sampling distribution of the sample mean for the quantitative GRE score for 16 students. Now, for this one, again, we're going to suppose, real quick, that instead of looking at an individual student, we're going to select 16. We're going to take all 16 scores, add them up, and divide by 16. That's going to be X bar. Okay? We want to find out what would the sampling distribution of X bar going to look like. So 3 things. When I say describe, what am I looking for? Well, first of all, I want to look at the shape. Well, this is only n equals 16. 16 is not greater than 30. But however, what do we know about the population distribution? We know the population distribution is normal. So what do we know about the sampling distribution? Well, the population distribution is going to be normal. So the sampling distribution is going to be normal regardless of the small sample size. Okay? So even though the population, even though our sample was only 16, our sampling distribution is still going to be normal. Okay? What's the center going to be? Well, first of all, let's remember the sample mean, the mean of the sampling is going to be the same as the mean of the population. So let's go back up at the top. What was the mean of my population? 150. So what's the mean of my sampling distribution going to be? It's also going to be 150. So that doesn't change. So the sample mean is also going to be 150. Now, what's going to happen to my standard deviation? Well, it's going to decrease. Okay? So the sampling distribution is going to be less, 8.8, okay? So 8.8 was the variability of the population. The variability of the sampling distribution is going to be less. How much less? Well, we're going to divide by the square root of 16. And what is the square root of 16? Square root of 16 is 4. So we got 8.8 divided by 4, and we got 2.2. Okay? 2.2. So we've got a new mean. The mean is 150, and the standard deviation is 2.2. So we have the same mean as our population, but our spread is considerably less. And our shape is still normal because the population was normal. Okay, so let's go to the second question. This is what we're doing tonight. What is the probability that a random sample of 16 students has a mean score on the quantitative portion that is less than 147? Okay, so first of all, we need to state the question. State the question. So here's what we're going to do to state the question. Oops. P. Now, I'm not finding X now, I'm finding a sample mean. So I want to find the probability, or I'm sorry, the probability, that X bar is going to be less than 147. So I'm no longer looking at my population distribution, I'm looking at my sampling distribution. Okay? This has changed. It's still 150, but my spread is no longer 8.8. My spread is now 2.2. So it's spread out a lot less. What is the probability that X bar is going to be less than 147? Now, the good news is we don't have to change much. We can go back. Let's go back to StatCrunch. We're going to change one thing now. In other words, I'm going to change this 8.8 to 2.2 because I'm no longer looking at a a population distribution. I'm looking at my sampling distribution. Now I got to change the sign to less than, and that's my answer. So notice again, my variability has gone down. So the probability that X is less than or equal to 147. Now, StatCrunch is not going to differentiate between X and X bar, but you can do that. So 0.0863. And of course, don't forget to interpret that. So step one, make sure you state the question. Two, and again, you can use z-scores for this as well. I can change 147 to a z-score and I can use the table. 147 minus 150 divided by 2.2. That'll give me a z-score and I can find that. And again, remember over here, I'm trying to find 147 and I'm finding the area to the left. That's how much is shaded in to the left. Cool?
Do we have to make that, do that for our homework?
What my curve?
Yes.
Yeah, you don't have to do the curve, especially if you're typing in your answers.
Okay.
Okay? Yeah, and again, normally if we were face to face and I was watching you do this, I'd probably have you do the curve just so you can see what area you're looking for.
Okay.
Okay? What is the probability that a random sample of 16 students has a mean score greater than 147? Well, you guys can probably figure that out. All I got to do is change the StatCrunch. I can reverse it, right? If I want to find greater than, all I got to do is change the sign. Everything else stays the same. Well, what's another way I can find that? Well, if I know what less than is, all I have to do is take that number and I can subtract it from 1, or I can just go back into StatCrunch and find it. So the probability that my 16 students will score higher than 147 is about 91.36%. So this is the same problem, only we just found greater than instead of less than. About 0.91 something, okay? Cool? Cool beans. All right. So let's look at this last one real quick. In the United States, the year each coin was minted is printed on a coin. To find the age of the coin, simply subtract the current year from the year printed on the coin. The ages of circulating pennies are right skewed. What does that mean that the pennies are right skewed ages? That means most circulating pennies were minted relatively currently, and extremely old pennies are rare. So my population distribution is not normal. My population distribution is skewed to the right. So the first question is, based on our information given, can we determine that the probability of a random selected penny is over 10 years old? I kind of gave it away. Why is it no? Penny ages. So if I asked you to find the probability that one penny is going to be over 10 years old, you wouldn't be able to calculate it because, well, our distribution is not normal. So I cannot find the probability that one penny is going to be over 10 years of age. Now, let's go down to this question. What is the probability that a random sample of 40 pennies has a mean less than 10 years? Has a mean less than 10 years. Well, let's figure out if we can do this one. So what do we know about X bar? Well, in this case, X bar is normal. What's our justification for that? Because what's our sample size? Our sample size is 40, okay? So by the central limit theorem, because n is greater than or equal to 30, X bar is going to be normal. So even though our population distribution is not normal, our sampling distribution is going to be normal. So now we just have to find the mean. What's the mean of X bar? So if we have a normal distribution, we need our parameters now. What's the mean? Well, to find the mean, I got to go back to the top, right? What was the mean?
12.2.
12.2. So what's the mean of my sampling distribution? It's also going to be 12.2. Now, each individual penny varies by about 9.9 years. Well, how much will a sample mean of 40 pennies? How much will that differ by? Well, considerably less, right? So how do we calculate that? We're going to take 9.9 divided by what?
12.
What's our sample size?
Oh, 40.
So we're going to take 9.9 divided by the square root of n, the square root of 40. So 9.9 divided by the square root of 40. You guys can't see this, but I have my calculator up on the screen. That's about 1.57. So each individual penny will vary by about 10 years, but a sample of 40 pennies will only vary by about 1.57 years. 1.57 years. Okay, so that's it. So now that we've got our new mean, we've got our standard deviation, now we can actually calculate the problem. So now I need my 3 steps. What are my 3 steps? First of all, we're going to state the problem. What is the probability that X bar is going to have a mean of less than, was it less than 10 years or more than 10 years? Less. We stated the problem. Now we're going to calculate it. This is step 2. We're going to calculate it. I'm going to use StatCrunch. Now again, you can use the z-score, but I'm going to speed this up a little bit by using the StatCrunch. Okay. So I'm going to go to my StatCrunch. I'm going to put in my new parameters, 12.2 and 1.57. Hold on, there we go. All right, so 12.2, 1.57, and I want to find the probability that it's going to be less than 10 years of age. Okay? And that's my probability, 0.0805. That's it. And then you can figure out what C is. If I want to find the probability that X bar is greater than 10 years, well, I can just take 1 minus the value that I did before. Okay. Or you can just put that back into StatCrunch and you just reverse the sign. You should get back 0.95. Cool. That's it.
So one last question for saying. So the problem that you just did, was that for the first question? Because the second question you did, that wasn't hold on. Based on that first question. Oh no, wait a minute. What did I do?
So let's go back to the first.
Oh, okay. Not that one. The second question, but I was referring to part B. That's what I meant.
So for part B, again, we just had to figure out what we had to be able to describe it. So we needed a shape. We needed a shape, and we needed a center, and we needed a spread. Okay. Now we can only find probabilities from a normal distribution. So that was important to make sure that we knew that the shape of the sampling distribution is normal.
Right.
Even though our population distribution is not normal, it was skewed right.
Mm-hmm.
Our sampling distribution is going to be normal because our sample size was greater than 30.
Okay.
if it wasn't greater than 30, then we would have to, we would need additional information. We'll show you that a little later. What happens if n is not greater than 30 and our population distribution is not normal? It doesn't necessarily mean we can't do the problem, but we're just going to show you some additional information that you can use.
Okay.
We'll do that a little later. Cool. Hey guys, that's it. I got you at 9 o'clock. I know it's a little over, but that's it. So let me show you real quickly what I have for the homework assignment up there. Again, I posted it. I'm going to actually put that into the assignment so that all you have to do is just do the same thing you did last week. So you can just do the assignment and just send it back to me. And this won't be due until Monday again. Okay. So let me pull that up for you. It looks like this. Okay, it'll be chapter 8 practice problems, and I'm going to put that into the assignments and instead of face-to-face. It'll say chapter 8 practice. It's not up there yet, but I will put this up there right after the class. And you're only going to be doing the first section, which is 8.1, where it says sampling distribution of a sample mean. That's these problems here. When you get to here, this is what we're going to do on Thursday, which is 8.2, which is sampling distribution of a sample proportion. Tonight we did sample means. On Thursday, we're going to do sample proportions. Okay? If you have any questions, like I said, you can always email me. If you guys want to do a Zoom, I can do a Zoom. But for right now, like I said, you guys got a couple of days to just look over 8.1, and then I'll answer questions about 8.1 before our class on Thursday. Cool? You guys have yourself a good night. Relax, stay safe.
You as well.
And I will see you guys on Thursday.
Okay.